let's start. So I'll basically talk about thinking in terms of, if you just think of modeling microtubule dynamics and try to understand the dynamics of microtubules. How do we go about doing this? This is what I will try and do today. So it will be pretty much complementary to the first lecture of the morning, the most of the part. So depending on the time, I will try and discuss why microtubule is a machine that can convert chemical energy into mechanical work. So Gautam said that molecular motors are machines that convert chemical energy into mechanical work, and yesterday we had a brief discussion. Microtubules are actin, the polymers themselves are machines that can convert chemical energy to mechanical work. So it has two parts. One is the chemical kinetics, and the second part is the energy transduction. So depending on the time, at least we'll cover the first part, and if there is time, we'll cover the second part as well. So this is what I'll try and discuss today. So, okay, before going to the next slide, so let us think of, from a very simple point of view. We all know a lot of things about experiments and all that. Now we were to sit back and think, what is the simplest model to understand any polymerization dynamic, any things that polymerizes? This is just one filament, and you add monomer to this or remove. So only two. When you think of a simplest picture for polymerization, this is what one comes to everybody's mind. So you have a simple, very simple polymer like this, and you can insert a monomer here, remove a monomer here. Right? This is the simplest thing you can think of. So this is something like analogous to quotes and quotes bias random walk. So Gautam said random walk, which is purely completely random. Here there is a bit of bias. The U and W, the insertion rate and removal rate, they are different. So there is if U is larger than W, there will be more insertion and less removal. So it's more biased towards the growth. There could be a situation where W is larger than U, which is the removal rate is larger than okay, so there can be when U is larger than W or W is larger than U, it could be either polymerized or depolymerized, which you could think of. And both the cases it is biased. Either it's biased towards polymerization or biased towards depolymerization. So if you were to think microtubules or even actin as such simple polymers, is it okay? We will see that it is not okay. So why is it not okay? So let us see. So if you just think of this, and if you think of the growth velocity, how fast it will grow. So if there is insertion, let's say 10 monomer per second, and removal 5 monomers per second, on an average you are adding 5 monomers, so it will grow in like 5 monomers. So the simplest, the growth velocity, which is how does this length change? I wrote here dl by dt. How does the average length change with time? It can be shown that it is just the growth rate minus the depolymerization rate, U minus W. So if this is the growth velocity, what does this immediately mean? So now, let us think a bit about this U and W. U is the growth rate. And this growth rate would depend on how much monomer concentrations available and so on. So you all know that the more the monomer concentration, more the monomers available, the faster it will grow. So U is actually a function of, U can be written as some constant K0 times the monomer concentration. And if you write like this, the V is nothing but K0 C minus W. Now you know that if you plot V versus C as a graph, you all know this, like it's a straight line, right? If I were to plot V versus C, the growth velocity of microtubule or even actin as a function of concentration, what you would get is a straight line. This is what you expect, because y is equal to mx plus minus c like equation. Now, many years ago, people did this experiment, and this is what they got. So when they plot, this is basically experiment from Marie-France Callier and Terence Hill and so on, collaborators in '84, and they got two lines, at least two slopes. So you can see this is one part. So here is velocity in the y-axis and concentration in the x-axis, and this is one slope, and there is something else. So it is clear that this equation we wrote, which is just one line, cannot surely explain what is seen here. You need at least one part here and another line here. So the simple model of polymerization, depolymerization will not explain this kind of velocity versus concentration behavior, right? So you need something more than that. So now we can also think of a little bit of, but however, so you need something more than that. We'll go and learn what we all know, that actin and microtubule has the GTP or ATP binds to this monomers and hydrolyzes and so on and so forth. So if you take into account all that, then only this can be explained. I'll come to that. But even before that, with the simplest picture, let us try and understand how much force one can generate from this kind of a polymerization and depolymerization alone. So if I write, so how do we think of generating force? There's a lot of single molecule experiments that people are trying to do to understand how much force actin or microtubule can generate. And one of those experiments is like this, where you fix one end of the polymer to somewhere, and the other end is growing, and you have some kind of let's think of a wall here. You have a wall here which can move, and you apply a force F here, and if this is to polymerize, it has to insert a monomer here and push the wall. So it has to do a work against this force F to polymerize. So then if it can polymerize, it can do work. So in this way, given an F, how fast this will polymerize? The rate of polymerization now will depend on the force F. So it turns out, to understand this, so we have only two events again, polymerization and depolymerization. And you have a wall that can move, and there is a force Fu that exert, that is external force, and this is trying to polymerize. To polymerize one unit, it has to push this wall by this distance d. So it has to do a work at least Fd, energy it has to spend to push this. So the rate of polymerization, to insert it, it has to do some work. So the rate has to decrease. So it turns out that the rate, which I said u, now which I said first K0C, will decrease further because it has to do a work against the force, and due to some kind of detailed balance that Gautam showed, the simplest form it can take is e power minus energy. So e power minus Fd by Kt. This is the, yeah.
So the model you are explaining of generation of force during the polymerization.
Yes.
It seems that the monomer which is going to be inserted.
Yes.
When you are applying external force.
Yes.
The monomer should apply the force.
Yes.
Not the polymer which is already polymerized.
Yeah.
But the monomer unit should apply the force.
Yes.
But that has no any rigid base. So how a suspended monomer can apply a force against external force?
So the rigid base is this fixed polymer. So it has to bind here to this fixed. So this whole polymer is fixed. So it has to bind onto this fixed.
But the binding side is already spherically hindered by the.
Yeah, good. So this, I said the wall that fluctuates. So this is something called a Brownian ratchet mechanism, where this wall has to fluctuate due to Brownian motion. So if you think of a membrane and an actin filament or microtubule which is like this, due to thermal fluctuation, this membrane will fluctuate a bit. So at some point there will be a time where there is enough space for this monomer to bind. So it can bind. So that is one way of thinking about it. Essentially, it would have done a work of, and then once it binds, this membrane will be like this.
sir, exactly it will depend on the concentration of these monomers in
Of-
the solution.
Yes, it will depend on concentration and the force. So if I were to apply like large amount of force, it cannot fluctuate. It cannot go this way, right? So it will depend on both on the force and the concentration. Yeah. If I were to push this very hard, it cannot fluctuate towards this end. So it cannot. Yeah. So that is the reason. So this is the simplest way of understanding. So if I put in this fact, U is K0C e power minus FD by KT. So you know that V is U minus W, and if we take U is equal to K0C e power minus FD by KT, what we get, so let's look what we get quickly. So what we have is V, which is K0C e power minus FD by KT minus, this is our growth velocity, and now this depends on the force. So people plot velocity versus force. So this is called force velocity relations, and this is a standard thing that measure both in polymerization or even for motor motion. You plot how does the velocity change when you apply a force F, and you can see that from the simple case it will exponentially decrease. Now I put the force in this on rate and the polymerization rate. One could put as well in the depolymerization rate. Then the curve would look something like this, and we don't know where. So it turns out that one cannot say the force is in on rate or off rate just by the equilibrium. The thermodynamics does not prevent it going from either way. The only constraint is that the ratio of on rate to the off rate, that is the U by W, should have this particular relation that it has to be e power delta E. Maybe I am missing a sign, plus or minus, one has to check it. But the off rate by on rate has to have this particular relation. This is called Boltzmann condition, or so one has to this has to be satisfied. Once this is satisfied, the force can be either in the off rate or in the on rate or both. So one can distribute the F, some part of it to the U and some part of it to W. So it is possible, but I'm showing the simplest picture here. So if this is the way it polymerizes, the velocity, if this is the force velocity relation, one can think of the maximum force such a machine could generate. So the maximum force is, so what will happen? Let us think this F, experimentally if you could increase F little by little, after some time it cannot polymerize. So the velocity will become 0. So the force at which the velocity becomes 0 is the maximum force or stall force. So this stall force, if you just equate this V equal to 0, so if you put this equal to 0, we will see that the stall force you get, let's do the algebra, what you get is minus kBt by W by K0C. So this is for the simplest case, if you know the K0, which is the intrinsic on rate or polymerization rate, and if you know the K0, and if you know the concentration, and if you know the off rate and the size of the monomer, the stall force can be computed. Okay, so this is a polymer which just polymerizes and depolymerizes in the simplest picture can generate this much of force depending on the W and K0 and C and all that. Okay, so another quantity that is observable or it can be measured in experiments is that when it polymerizes, it also depolymerizes. So if you just think of the tip of this polymer, most of the time, if I plot the tip position, X tip is a function of time, you can see that it increases and a little bit it can fluctuate. Polymerizes, depolymerizes, it can fluctuate. For microtubule, you saw that it can fluctuate quite a bit. So how much this fluctuates? It can be measured. So if L is so let me call this L. L is the length, or the length the same as the position of the tip. If I take L as the length of this, one can calculate a quantity called L square average minus L average square. Just like Gautam said, R square average minus R average square. So this is the standard deviation square. This is the variance. So one can calculate such a quantity, and it will turn out it will be a time dependent quantity here. And if you look at it for after a long time, it will turn out that the sigma square is proportional to time. Just like Gautam said for diffusion, R square average minus R average square was 6 dt. So here this is a 1D polymer. So this will be 2 dt. So this will be 2 and some constant times gt because it's 1D. So one could think of this constant as something like a diffusion coefficient, and this will be nothing but if this is the equation, if I take the derivative with time, what I wrote here, half d sigma square by dt, one could get this quantity, and this will depend on this on rate and off rate. For the simplest model, it will turn out to be this u plus w by 2. So for biased walk, with u as the rate to go forward and w as the rate to go backward, this diffusion coefficient will turn out to be u plus w by 2. Okay, so this is so one can calculate all kind of measurable quantities nicely for the simple model. But of course, the simple model is not correct for either microtubule or actin. So now, let us go ahead and, so do you have any question on this so far, like this, for the simple model?
You told us about the stall force.
Yes.
The maximum force after which the polymerization will be hindered.
Yes.
So the external force, which is called as the stall force, will just hinder the polymerization, but the depolymerization rate is not being affected by the stall force.
Okay.
So why should stall happens at all?
Okay. So as I said 1 minute ago, we don't know the force. We only know that we apply force. We don't know what happens. So it can be that the force. So we have two rates, U and W, polymerization and depol, and we don't know what happens to this force. So the force. So without the force, let me call this with some number W0 with no force, and this is the polymerization with no force. Now the force that you apply, a part of the force can help depolymerizing. It can happen. So it can so happen that the force that you apply, a part of this will be preventing polymerization, as I said. So I could write in general minus alpha f by kt, fd by kt. So alpha is a fraction between, alpha is a number between 0 and 1. So let's say alpha is half. Half of the force is gone to decrease the on rate. The remaining 1 minus alpha, this will be again half if alpha is half, could help depolymerization. So this is plus f here. So this will be, the more the f, the more the w will be. So we don't know. So now, irrespective of alpha, the stall force will remain the same. You can see this. You can use this u and use this w and write v is equal to u minus w and take v equal to 0 and calculate. The f will be exactly the same as we calculated before. So it doesn't matter what the force does, whether it is helping depolymerization or preventing polymerization, the stall force will remain the same.
I have a question.
Yeah.
So the force exerted by the polymer on the fluctuating wall, will it be by the monomer only, which is just being added, or it would be the composite force of the whole polymer?
Monomer sitting on the fixed polymer. If there is nothing to be fixed in the back, if this is not a rigid wall to fix here, Newton's third law says that it cannot move, right? You need some place to.
Yes.
So it doesn't just depend on the monomer alone. It has to also have this polymer which is fixed at a place and all that.
But the force will not keep increasing with the length of the polymer.
No, the force does not.
Of only one monomer.
The force depends only on these rates. So the maximum, the force. So we will see. So if we have this, the force, the maximum force, for example, depends only on this. Did I have it somewhere here? So it only depends on, doesn't depend on the length. It only depends on the rates of polymerization and depolymerization. Yeah.
But it needs to have space to polymerize and depolymerize. So
Yes.
basically, the space availability should take place before the polymerization.
So this is what I was saying about Brownian ratchet. So this wall which I showed here, this is, if you imagine this is a membrane that fluctuates and that creates the space. That is the Brownian ratchet model. The Brownian motion would make the wall fluctuate and that would make some space for the monomer to insert. Okay, so now we will go to the little more correct picture as far as the microtubule or actin are concerned. So you all also know that there is this famous thing called dynamic instability for microtubules where they grow and shrink rapidly. So many of you might have seen this famous movie which is there with the CD of the book Molecular Biology of the Cell, or even YouTube, where the microtubules grow and shrink rapidly. And if you look at the length versus time, it can look something like this, where it grows and shrinks rapidly. So this is called catastrophe and rescue, and most of you know. So I'll just quickly go to the next slide, because if you don't know, you could ask later, and you heard in the morning. So the model we said cannot explain the velocity data, cannot explain the length fluctuation, and cannot explain the treadmilling and dynamic instability. So length fluctuation, I mean including dynamic instability. So none of this can be explained by the simple model. So we need to have a little more realistic model, and which looks something like this. So here to be ATP / GTP hydrolysis. If it is actin, it is ATP hydrolysis. If it is a microtubule, it's GTP hydrolysis. So but the model is like this. So you have a set of monomers, and typically as you all know, that it is associated with microtubule monomer is bound with GTP, and it can so GTP bound monomer is what is shown here. Because T stands for GTP or ATP, depending on whether it is, depending on if it's microtubule or actin, and it can polymerize with some rate U, and this can depolymerize with some rate WT. Now it's not just W, it's WT, where is the depolymerization rate of T bound monomer. And this T can become D with some rate R. So this is the hydrolysis of ATP hydrolysis or GTP hydrolysis. And once everything is hydrolyzed, you might end up something like this, where everything is D. Here in this slide, there is an assumption, which is this hydrolysis happens in a vectorial manner, that is this T. So this in a very sequential manner. The hydrolysis happens in a sequential manner. There will be another case where hydrolysis happens in a random manner, which I will discuss briefly later. But let us think of the simplest model again for this case, which is the hydrolysis happens in a very sequential manner. The one in a very vectorial or sequentially, this T gets hydrolyzed to T. So you would end up with such a picture. And it turns out that typically, if you have such a case, you have a polymerization rate where a T bound monomer can be polymerized, and this D bound monomer can depolymerize with the rate WD. So remember, see here, WD is different from WT. So WT is the depolymerization rate for T bound monomer, and WD is the depolymerization for D bound monomer, and these are very different. And that can lead to a whole set of phenomena, including dynamic instability, and this also breaks the symmetry. So you can, at this end it is more T, and this end it is more D. So this can also lead to treadmilling. So this is the simplest model that will give you all sorts of phenomena. And if you analyze this model in detail, it turns out that you will end up with, so of course this can give all this phenomena, and this is not only in microtubule, various other param and various other things this can show, and it depends on ATP hydrolysis, so which I wouldn't discuss now. And it turns out that if you have such these events, U, WT, WD and R, this is like a random walk in a 2D plane. So simplest model I said is like a biased random walk in 1D. It turns out that this is a biased random walk in a 2D plane, and if you are interested to understand how is it in 2D plane, I'll tell you this later, but it turns out that this is what it is. And if you analyze this little more, it turns out that there are three kinds of growth, or if you look at the length versus time data, you can see three kinds of curves. One is rapidly growing, is blue. Second one is this red. It is on an average it is growing, but once in a while it shrinks. And the third one, it is kind of bounded, where it is not really growing, but it fluctuates. So one could get 3 different cases depending on this 4 rates. So we had 4 rates here. So we have 4 parameters. So the 4 rates we had are U, WT, hydrolysis rate R, and WD. So depending on this value of these 4 parameters, one could get any of these 3 in the model that I said. So one could either get a rapidly growing phase, the polymer grows very fast, or on an average it is growing but not so fast, but there is some kind of shrinkage happening, and it's not growing on an average, it fluctuates. So it also turns out, so one thing which you all probably know, this part is called cap.
Sorry, one interrupt.
Yeah.
You talk about how you made these models at some point during the tutorial today, or how was these models were?
Okay, what is the basis of this model?
And also how you do these simulations?
So simulation I'll talk you after the end of this. I'll talk how the simulation is being done. There is a bit of theoretical analysis to understand these phases, which I won't talk today, but either you could read in the paper or maybe some other time we could discuss. Yeah.
So the model which you have shown, from that model only you have got these 3.
Yes, this is direct consequence of this model. So this model where you have 4 events, which is U, which is the binding, WT, which is the depolymerization, and WD and hydrolysis. So this 4 events immediately would lead to this kind of phases.
According to this model, when a polymer is going to bind to already formed polymer,
Yeah.
the force is applied.
No, there is no force as of now. What I'm saying is,
Off rate and the K off and K on that you mentioned, that K on is the force constant that is which is used when the monomer is going to bind to the full polymer.
so we are talking about only rates now, and these rates could be depending on the force. So this can generate force, but whether there is force or not, I'm just, at the moment, I'm saying that there is this polymer, and things will bind, dissociate, hydrolyze, and all that will happen with some rate, U. The U could depend on if there is a wall, this U will be depending on, and if there is a force applied, if there is a membrane, if it is near a membrane, and if there is some force the membrane cannot, then it will depend on the force. If there is no membrane, if it is in vitro some situation, none of this will depend on the force. So this is a very general model. I am just talking about 4 events happening with some rate, and these rates could in turn depend on force.
Do you have evidences that GTP bound monomers or these tubulins undergo this depolymerization? Because according to your model, even GTP bound is undergoing depolymerization.
Yeah.
But we have not seen.
Okay, so in microtubule, there is this controversy, kind of a controversy, which says that the depolymerization rate for a GTP bound monomer, so there is a 500 times range of it starts from something like 0.1 or 0.01 per second, monomer per second, to 20 or 30 monomer per second. So there is a range of values. But however, if you do not, so the very fact that there is a critical concentration for polymerization immediately would in turn mean probably that there is depolymerization. So there is some depolymerization. How small it is, we don't know. So it might depend on the various conditions, temperature and all that. So there is experimentally, when people measured, there is a huge range, 0.1 monomer per second to about 20 monomer per second. So there is a huge range of depolymerization rate. However, there is some WT.
Whenever we say about critical concentration, that critical concentration includes heterodimers GTP bound, right?
Yeah, yeah.
Not with GDP, because that can undergo polymerization.
Yeah, so there is not this would immediately means that there is also some kind of controversy regarding critical concentration of microtubules. What exactly is the critical concentration? People kind of debate. So there is some questions related to critical concentration which I might address later when we come to that. But given that what I am trying to say here is that one could take 4 rates, U, W, T, R. What is the value? We are not worried at this moment. It could be very close to 0. It could be as small as 0.01. Still the model is correct. Everything what I am saying is correct. But there is some value for all this. These values could be very small or large. Okay. So depending on what the value is, you will see any of this phenomena. So if the values are different, you would see like some kind of, if WT is depending on if U is very, so I'll show you in a minute. If U is very large, you will see the blue part. If U is not that large, it's somewhere in between, you will see this curve. And if U is very small compared to other rates, then you would see this. So there are various phases. I wouldn't go into the details of these phases, but it just for this purpose of this talk, it is sufficient to understand that one could see these 3 kinds of phases. And okay, now let us think of this for a moment. This fact that there is T and D. So there is T here, there is D here, and after hydrolysis, at some point it could be D. It could be at some point of time it could be like this. Everything is D. So if you have such a situation, and if you think of this velocity, growth velocity, what will you conclude? What will be the growth velocity for such a polymer? So when there is T can polymerize and T can depolymerize. So whenever there is a cap, the growth velocity will be just polymerization rate minus depolymerization rate. However small it is, it will be just U minus WT whenever there is a cap. But if there is no cap, it will be polymerization of T or depolymerization of D. When there is no cap, it is, so if there is a cap, so with cap, and if there is no cap, it is this. So one can calculate the probability that there is a cap. So if you call something called PT, probability that there is a cap at the end, if you know this quantity, so there is polymerization, and whenever there is a cap, which is a P, it will depolymerize with the rate WT, and when there is no cap, it will depolymerize with the rate WD. So 1 minus PT is the probability that there is no cap. So PT is the probability that there is a cap, and 1 minus PT is the probability that there is no cap. So whenever there is a cap, it will depolymerize with this, and whenever there is no cap, it will depolymerize with this rate. So this will be the one can think of velocity as this, and it can be rigorously shown that this is indeed the formula for velocity. And if I do that, so this is what I wrote here. So one can show that for such a model, the velocity has this particular relation, and I intuitively said that it has to be like this. And it turns out that this PT, that is the probability to have a cap, if there is large amount of monomers, T-bound monomers, it's likely that there will be a cap. So when the concentration is very large, the PT is 1. But when the concentration is not that large, the PT has this particular form, which again one can intuitively think of, which I would not discuss now, but it can have this particular form. So this immediately means that for large concentration, PT is 1. So for large concentration, what you would see is that K0C minus W. For small concentration, you have V is K0C minus WT times PT also has C. So look at here, this PT has concentration in this. So there will be another concentration here, and minus WT into 1 minus PT This also has concentration. So if you plot velocity versus concentration, the plot we saw, for large concentration it will be one line with a one slope k0. For small concentration, it will be a different slope because there is a C. So if you look at, this is the curve for actin, this is what I am showing, and it can same thing for a microtubule. For large velocity, this dots has this relation which is k0 C minus W, but for small concentration, it will be a different formula which is this. And it turns out that it will fit nicely for actin and it can be shown for microtubule as well.
In this plot, we are saying that at a small velocity,
Yeah.
the slope is blue line.
Yes. For small concentrations,
So yeah, a small concentration.
yes, the slope is blue line, which is given by this formula, which I just, this blue formula there.
Which is stating that the velocity is high.
No, velocity is whatever the small, the number, what you see there. But this is it is a different slope. The reason is that, as I said, previously the slope was determined by this factor, right? So only K0 was the determining factor for large concentration. But here, this PT, which is the probability to have a cap, comes into picture. And this PT has the C there. So if you substitute this PT into this formula, the C will have different factors like K0 by WT plus R and so on and so forth. So it will have a different slope. So this will nicely explain the force velocity relations.
So at high concentration, the instability is reduced.
Yeah. High concentration instability should be reduced according to this model. Yeah. Okay. So let's go ahead because all of you might be hungry soon. So let me. So one can show various things like length fluctuation, how large it is, and it will show that this model will show that the length. So what is plotted here is the average length and the standard deviation, and both are equally big. So the length fluctuation is as big as the average itself. So which is the typical thing of dynamic instability. So dynamic instability is a phenomenon where the length fluctuation is as big as the average itself. Now, one other interesting thing that you want to note is that when I plotted this bounded phase, it looked like this. For microtubule, it looked like this. They are slightly different. See here, there is a sharp catastrophe, means there is a sharp decrease in length. And here we don't see, it's more like this part is more like a triangle. Like the slope here is same as this. So the model I said as of now doesn't show the kind of behavior, if you look at the minute detail, it looks very different. So it turns out that to get this kind of a length versus time graph, one has to add one more ingredient, and which is this. So when this polymerization happens here, when a monomer polymerizes to a D end, it has to have a different rate UD, which is much smaller than the polymerization rate here. If you put in this fact, which is true for microtubule, the polymerization to a D end is rare. If you put in this fact, immediately you will get very sharp fall, which is very much like this kind of a thing that you see. Okay, so you need one more ingredient to explain the microtubule kind of length versus time. And I'll now quickly go to a different model of hydrolysis, which says that the hydrolysis could happen. So I said vectorial model where the hydrolysis happens in a sequential manner. This T will hydrolyze after the next hydrolysis will be this particular T, but nobody knows what is correct. So it could also happen that randomly they could hydrolyze. And if you assume this random hydrolysis model, everything else will remain the same. Pretty much all the results we will get, except that couple of things will change. And one thing immediately will change is the cap size. So if you look at the concentration versus cap size, what this random hydrolysis model will say that the cap size will saturate. So you can think of this little bit intuitively. If you think of this vectorial model or the sequential hydrolysis model, so you have some cap here, this is all D, And with some rate, this t becomes d. So let's say 5 per second. Every second, or 1 per second. Every second, 1 of this t becomes d. But if the polymer, if there is a large concentration of t-bound monomers in the solution, they would polymerize much faster than they hydrolyze. So if that happens for very large concentration here, polymerization will be much larger than hydrolysis, because hydrolysis doesn't depend on the concentration. So then one would get a very large cap in this model. But if you assume that random hydrolysis, and if there are many T's, and I say that the hydrolysis rate is 1 per second, after 1 second, all of this got hydrolyzed. So hydrolysis will happen exponentially fast. So all of this will hydrolyze within a time of 1 over r, the hydrolysis rate. So that would immediately mean that the cap size will come down. So if you look at here, this is the estimate for microtubule for the rate that we know. And this is for a 1 filament picture. So this will come out to be like close to 20 monomers. So if you think of this as a ring, this will be like 1 or 2 layers of cap. That's what these rates will say. So immediately this random hydrolysis model indicates that the cap size will be so, and people more and more believe in this kind of random hydrolysis model, where people think that this is correct. So most of the things except cap size and few other things are same in both the models, but this is the more preferred model these days, that the hydrolysis happens in a random manner. Okay, so yeah. Yes, any of those T's randomly. Yeah.
What we have learned so far is that when there is a GTP bound beta tubulin, and when the heterodimer comes, as soon as it binds, there is a GTP hydrolysis. So always the terminal heterodimer will have GTP, and as soon as the next one comes, the penultimate will do the undergo hydrolysis.
So as far as I know, I don't know the details of experiment. There is no real proof, so which would mean that whenever there is a binding, there will be a hydrolysis. So they are coupled. I don't know if there is any proof for this, but I am not aware of. There is a clear proof, because as far as I understand, there is no clear proof for this can happen. And there is actually about 2009, there is a paper by Frank Perez from Institute Curie, where they really use some kind of fluorescent label to see the GTP bound cap. I don't know if this is reproduced or what, but there is a science paper you can look at from the group of Frank Perez. I think it's 2008 or 9. Maybe I have it here. So let me just see if I have it. I had just saved it for all of you to see, but okay, I don't have it here, I think so. Okay, so anyway, so you can look at this, where they really see that there is some cap even within the microtubule.
Actually, sir, in that paper, they have said that those sites can actually act as the sites where rescue happens.
Exactly. So, which indicates that this may not be true. That is, when it binds, it may not immediately hydrolyze. Okay. And a few other things like, when does the catastrophe occur? This is another question that people all ask. And theoretically, people all think that people used to think that whenever this cap is lost, the catastrophe will happen. So you have such a cap, and whenever this cap is completely hydrolyzed or lost, immediately the catastrophe will happen. So in this case, think of this: if this T, both these T's are lost, there is a D, and if this D depolymerize, there is a T again here. So this may not lead to a catastrophe always. So if you assume that whenever the cap is lost, it will lead to a catastrophe, that would lead to some kind of inconsistent results. And what is shown here is the catastrophic time versus concentration. If you assume what I said, if you assume that whenever the cap is lost, the catastrophe will happen, you would get this kind of a catastrophic time, which is 1 or 2-3 seconds. This is catastrophic time in seconds, the y-axis. And what is the plot on the right hand side shows that the catastrophic time as a function of concentration, and what you would get is a few seconds. If you calculate according to this model, which assumes that whenever the cap is lost, the catastrophe will happen. But just let me complete this. But this is the experimental points, this red dots and circles, which shows that few hundred seconds is the catastrophic time. This is a red dots from experimental paper by Jansen et al., which is basically Merlin Doctrum's group. They show that it's a few hundred seconds, and the only way to explain this, it turns out that to assume that cap losing is not enough to have a catastrophe, you have to have a few number of D monomers immediately after at the edge. So the edge should have, this case for example, here is only one D monomer at the end. This would lead to a catastrophe. You have to have at least few D monomers, and if you make that assumption, it will give the TC of the order of that is experimentally measured. Yeah.
Catastrophe is a depolymerization of
catastrophe is not just depolymerization.
Sudden
decrease in length.
Decrease in the length.
Yeah.
That is due to depolymerization.
Yes, this is due to depolymerization.
So here we are plotting depolymerization and what is catastrophic time with respect to the.
So Dulapana was saying today morning, catastrophic time basically is the time needed for the catastrophe to happen. So let us look at this here. So let's say a rescue happens, it starts growing, and here the catastrophe happens. The time between these two can be thought of as catastrophic time. So time for the catastrophe to happen. So you could think of roughly as time between two catastrophes. So one catastrophe happens here, next one happens here. So it could be thought of even as a time between this. So there is some definition which people define in different ways, but roughly it means that the time after a rescue, how long one has to wait for the next catastrophe to happen. Okay, so this is about the vectorial model. So one can do a Monte. So now I'll quickly in 10 minutes I'll stop with this. It's already like 1:10. Okay, so I just simply tell you for the simplest model that we thought of, where it's just polymerization and depolymerization alone, how will you do a simulation? So to get the length versus time graph, what one has to do is some kind of a simulation called kinetic Monte Carlo simulation. And we'll discuss for the simplest model, and this is based on an algorithm by Gillespie, which is published in this paper. So I'll briefly tell you what exactly is this Gillespie algorithm and how do you calculate this length versus time for for any polymer for the simplest model, and you could think of for this little more complicated model. Okay, so first thing is so when you say polymerization and depolymerization, it is like a chemical reaction if you think of it. So what you have is a polymer, and then you're adding a monomer. So this is a polymer of 5 monomers, and this will become a polymer of 6 monomers. So 1, 2, 3, 4, 5, 6. So, and this can go both ways. So this is the polymerization rate, and this is the depolymerization rate. So Gillespie said like any chemical reaction can be simulated in this particular way. So the first thing to know is that what are the events, quotes and quotes, events happening. The event here is polymerization and or depolymerization. Two events happen in this simple case. So these are the events, polymerization event and depolymerization event. So first thing in the Gillespie algorithm is to figure out in the system you have what are the events. So in this case there are 2 events. In the previous case there are 4 events. U, W. So associated with each event there will be some rate. Here there are 2 rates U and W. So if you know these rates, so we have 2 events here, addition of a monomer or removal of a monomer, or if you think of a molecular motor, this could be moving forward or moving backward. Exactly this picture can be thought of for a simple molecular motor motion. There will be 2 events which is moving forward or moving backward. And the first, so we have such a polymer which has 5 monomers, and we know that the length is at this particular time. So we know this t equal to 0, the length is 5. Now the question is what will happen next? Will it polymerize or depolymerize? So how do we decide that? So it is decided by based on this rates. So we have rate of U and rate of W. So let's say U is 10 per second and W is 1 per second. So most of the time you intuitively know that polymerization will happen. Rarely depolymerization will happen. So this rates is proportional to the polymerization probability. The probability to polymerize, let me call it polymerized probability to go forward, is proportional to this rate of polymerization, and probability to go backward or depolymerize is proportional to this rate W. Right? Intuitively you know that this has to be the case. The more the polymerization rate, it has to go forward. More the depolymerization, it has to come backward. And only two events, so just PF plus PB has to be 1. The total probability has to be 1 because only one of these two events, either it has to polymerize or it has to depolymerize. So based on this, it will turn out that the PF is U by U plus W and PB is W by U plus W. This is the only way you could write this. Right? This three equations would tell you that this is like this. And now the question is, so you know the probability. Let's say, you know, U, let us take, for example, U is some number. Let's take U as 5 and W as, let's say 3 and 2, right? So this is PF is 3 by 5 and PB is 2 by 5. Okay, let me take a little differently, like 4 and 1, so that is easy for us to. So this is 4 by 5 and 1 by 5, which is 0.2, right? And this is 8.8. So what does this tell us? This tells that 80% of the time it will go, polymerization will happen. 20% of the time depolymerization will happen. So one has to use some kind of trick so that the simulation 80% of the time polymerizes, 20% of the time depolymerizes. So the trick to do that is the following. So a trick to achieve this is the following. So in computer there is something called random number generator, where you can generate random number between 0 and 1. So let us divide this into few intervals. So this is 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9. So this is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So I divide it into 10 boxes. Then I randomly generate number between 0 and 1. Randomly. Let's say I generated 10,000 numbers, random numbers, and they are all uniformly distributed. So how many of them will be between 0 and 1 out of this 10,000? They are all uniformly distributed. 1,000 of them, right? So how many of them will be between 0 and 0.2? 2,000 of them. How many of them will be between 0 and 0.8? 8,000. So 80% of, so if you take the random number, if the random number is between 0 and 0.8, which will happen 80% of the time, you go forward. So if you generate a random number, if it is between 0 and 0.8, you do the PF, which is here according to what we got is 0.8. So based on, so you generate a random number, if it is between 0 and 0.8, you do the polymerization. Otherwise, you do the depolymerization. That will immediately give us 80% of the time polymerization and 20% of the time depolymerization. Right? So this is the trick that one can, to implement this kind of probability. So now you get any probability. If you get PF is equal to 0.4, what you would do is that if it is between 0 and 0.4, you would do the polymerization. Otherwise, you would do the depolymerization. So this is, if you have more events, you could do the same thing. You could divide this, and that many times, if between this and this you do this, so one can do this and you can think about it, one can extend this to many events. Okay, now we know which event will happen. You generate a random number, that will tell you what is the next event. Whether it, so we have this, to begin with t equals 0, it does in 5, and if the random number, you got 0.1 as the random number you generated, it is less than 0.8, so it will go to next it will polymerize. But when? So you have to get time. So it can polymerize either after 1 second, 2 seconds, 3 seconds. So when will the polymerization happen? So you have to also get information about the time. So it turns out that the way to get is this. So the fact there is some fact that the stochastic events has an exponential time distribution would mean that the time, the delta t, when will this event happen, is given by this particular formula, which is -1 by u plus w log of r. And this is, I can explain to you later where it is coming from. This is basically coming from the fact that the time has an exponential waiting time. What is the time delta t you have to wait for this event to happen? And this has an exponential distribution. And this is basically coming from that. And so this answers to the question, when will that event happen? The event will happen after a time delta t, which is given by this u and w and a random number. But if you do this, you will get all the physics correct for this. So we answered 2 questions: which event will happen and when will it happen? That's all we want to know. So we want to know either polymerize, depolymerize, when. So we get the complete time L versus T information. So this is the way to do this. So I think here I will stop the lecture. So we kind of saw the kinetic part. There is some mechanic part which I wouldn't discuss now, where how does the depolymerization of microtubule can generate force, and this can be also understood through a different kind of Monte Carlo simulation. So Ishutesh, who's here, he will have a poster on this. So you could go and see the poster where he'll have all the details. So I would only stop with the kinetics part, but seeing Ishutesh's poster, you will see that this can also generate force by polymerization. He will discuss how does the depolymerization generates force and how much force it can be generated and all that. Okay, so I'll stop here, and if you have questions, we'll discuss. Can you ask once more? What is that?
You said that the concentration, the rates are different, and the low concentration, the rate will be different.
Yes.
And the rates and concentration will be different.
What I said is that the PT, the probability to have a cap. So we said that if you have a polymer, what is the probability that there will be a cap? If the concentration is very large, like and concentration of T-bound monomers, GTP-bound monomers, if the concentration is very large, likely that they will polymerize. So then surely there will be a cap. So for large concentrations, the PT will be 1. But for small concentrations, there may not be a cap, because so then PT will be something different. And it turns out that for the simple model I discussed, it can be shown that PT has this particular relation.
Does this mean that a high concentration, the catastrophe will be less?
Yes. High concentration, the catastrophe will be less. That's what this model would at least say. And which is what shown also, seen also. Yeah, for very large concentration, the catastrophe. So you can also, there is this graph, experimental graph I showed. So here is catastrophic time versus concentration. So basically growth velocity also means the concentration. They change the concentration here. So large concentrations, the catastrophe, it takes long time to catastrophe to happen. Yeah.
Maybe it will be useful to tell the students at this point that Gillespie algorithm is useful when you have a mixture of slow and fast getting, let's say, slow and fast axons. Okay, it saves a lot of computer time, but there is another way of doing simple Monte Carlo simulation where you can increase your time step in fixed delta t.
Yeah.
Here the delta t is not fixed; it's taken from some distribution. But there is a simpler Monte Carlo simulation where you can have fixed delta t. This is to save the computer time, where you have a mixture of fast and slow and fast.
Yeah.
And then thus this is probably you read it, right?
Yeah.